when you have data, there's actually a data with how fast you can transmit information and how accurate the information is. The faster you transmit information, the more likely that one mistake goes up your whole series of data. A simple explanation would be if I say a long word, like bye, if I say bye, and you miss one bye, you probably can still hear the word bye and know that I'm saying bye. If I just say bye, which is a lot faster, just once, you miss one, it's over. The message is incomplete. And this is why in a lot of areas without a lot of good infrastructure, the internet actually has to be slower than you think it would be because it's less accurate too. You have the transmission is less accurate and a bunch of other reasons, which I'm going to go into it. And another reason why to promote good infrastructure in the first place and good data and stuff, because it's hard, because good data in the beginning means also faster data in some ways. But first let's go over some basic concepts. Well, most data is set in either ones or zeros. The simplest way and that everything approximates of making data more accurate, even if there's mistakes, is I repeat a sequence. So instead of saying 1, I say 1, 1, 1 3 times. Then if only 2/3 of the numbers at least has to change for it to be less accurate. In that case, when I repeat it 3 times. In case I repeat it 5 times, 3 out of 5 has to change. And you might notice it's going about half the size of the numbers. For 0, same idea. With this simple case, when I just take the majority, it goes with about half the size I've increased the thing. Or how much more accurate, or how much more likely to have a problem is 1 divided by n, where n is the size, or 2n. Now in different schemes, the radius kind different, but these all follow these general rules of an exponential decay, where you can take longer and longer to transmit the data, but it's diminishing returns on speed. Now one way to make this means that actually compression can make data transmission speeds a lot faster. Compression means if I compress my data, I store it in less data. So that first seems bad. I have less data, one mistake makes a bigger deal. But if I compress the data to a grouping, which I cannot do, twice the size, I can repeat the data 2 times. So if I do a 2 megabyte file into 1 megabyte file, I can repeat it twice and I get 2 megabytes. And if I have a mistake in one file, I have half the likely to have a mistake. This is a simplification, and it depends on what compression systems you use and all these other things. But it does hold true. The exact numbers vary a lot. Now, how does compression work? Well, there's 2 types of compression: lossless and lossy. So in lossless, we look for a pattern. And if we have a pattern, we can use that pattern to compress the data. So an example would be if I have the pattern 1 0, repeat it 10 times, instead of saying 1 0 1 0 1 0 1 0 1 0 10 times, I can say repeat 1 0 10 times, which might be a lot shorter. Even shorter would be repeat 1 0 a billion times for 1 0 1 0 1 0 billion, say instead of saying 1 0 billion times. But basically, I'm telling you some pattern that makes it smaller. Or I make another way of doing another way of doing it is I find something that's more common and I replace it with something shorter. So let's say that 1 1 appears a lot in the sequence, and so I replace 1 1 with 0, so then it takes less data. Or place place something that's very common with a short like side note. You can see this with acronyms. So if I know a word commonly appears often that's very long, I'll place it with a shorter word, and I can make the longer thing stand for something shorter. Saves data, and that's why we use acronyms. The problem with this method of compression is that the more data and the bigger data sets you have, the better it works. And the reason why it works better for bigger data sets is there's more patterns you can find, and there's more things they can find to sort abbreviate. In a smaller data set, it can even hurt your data, because in a small data set, if I only have 1 0 appearing once, for example, and say 1 0 appears once, that's longer than just saying 1 0. All compression, since actually can do the opposite and make something longer, especially if it's smaller, and compressions become more predictable the bigger your data set is. How does this affect people in with lack of infrastructure? Well, when data signals are transmitting, if they are transmitting in place with lacks of a lot of data and signals being submitted, you can compress the data less, which means you can speed it up less, or you can make it less accurate in those places. The other type is lossy compression, where I throw away data to make it smaller. Now, what data you can throw away and what data is important is more easily detected when you have a big data set, and you can find out what people don't use a lot, or what data is flowable but throwable. So it also helps there. Another one is method you can use is to tell if there's a mistake. And the idea is that if something is highlighted, it could be a mistake or it's definitely a mistake, you slow down and repeat setting the data again. So sometimes you keep setting the data fast until the message is nonsense. This also obeys the same limitation with speed as before, but it can get a little faster than you would normally. But still, if you implement it, it will have this like exponential decay with time. However, it's easier to tell if there's a mistake sometimes in a small data set, but oftentimes in a bigger data set, because you can see the outlier. It's like one number is way off compared to a billion other numbers. Compared when one number is big, but you only have two numbers, maybe it's the small number that's off. The more numbers they have, the easier to detect an outlier. So for that, same thing with infrastructure. Another thing is you can do the same thing with importance, in that you take data that's more important and you encode it more often, or use that data more. So you focus more on, so you don't worry about the accuracy of other places, and you repeat that more. But with that, again, the more data, the more things you can figure out what's important or not, which leads to overall faster speeds in the long run and more accurate. The other thing is when you have a big data set, the less is to make it so so there's less noise in the first place and less mistakes, and that's easier when you have more infrastructure. And all these things compound and work together for much faster speeds, potentially when there's more stuff there. Now, faster speeds doesn't actually mean faster. I mean faster transfer of like gigabytes or megabytes to you, but you might also be using more megabytes or gigabytes. So that could counteract this effect. It's like, oh yeah, you're fast. It's like you win less races even though you're faster because everyone else got faster too. Well, this is just a little bit off tangent compared to my user videos because it's not as direct, but it does have some ideas about why we need to build up infrastructure more rapidly. Well, thank you very much. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers a year and 4,000 watch hours, which is really hard, but with your help, I think I can do it. Also, if you have any ideas for future videos, any comments, suggestions, please leave them in the comment section below. Thank you very much. Goodbye.